Good evening. I'm Spot On Weather meteorologist Matthew Euler, and tonight we're going to take a look at a very important topic, teleconnection trends in sensible weather. I find this a very interesting topic, has great implications on our weather itself. So let's get right to it. Starting off with our presentation topics for this evening. We are going to take a look at the definition of a teleconnection, the teleconnection types and the general weather patterns, past historical winter weather associated with teleconnections. Just similar to the winter forecast, I'll be looking at most likely dividing this up into two parts. There's a lot of good information here that I'm going to present. All right, so let's start off with the definition of a teleconnection. What exactly is a teleconnection? A teleconnection, this is right directly from the AMS, the American Meteorological Society Glossary. A teleconnection is a linkage between weather changes occurring in widely separated regions of the globe. And many teleconnection types which impact the weather, there are many of those. There are many teleconnection types which impact the weather. These mainly impact the long wave pattern, jet stream, which influences surface pressure systems and temperature regimes. And we'll go into much more depth on that. Some of the teleconnection types we're going to discuss include the North Atlantic Oscillation, and that's usually abbreviated NAO, the Arctic Oscillation, which is abbreviated AO, the Pacific North American Pattern, the PNA, El Nino, Southern Oscillation, it's actually abbreviated ENSO, and the La Nina, which is a reverse of El Nino, and then the Madden-Julian Oscillation. All right, so again, the types of teleconnections we're about to go in depth on, again, include the NAO, the AO, the PNA, the El Nino, Southern Oscillation, La Nina, the ENSO, La Nina, and then the Madden-Julian Oscillation. All right, so let's first take a look at the North Atlantic Oscillation. What exactly does this mean? The North Atlantic Oscillation is based on sea level pressure differences between the subtropical, the Azores high in the Atlantic Ocean, and the subpolar low near Iceland, which is typically called the Icelandic low. Now, if the NAO is in a positive phase, we typically see below normal heights and pressures across the high latitudes of the North Atlantic, and above normal heights and pressure across the central North Atlantic, most importantly, the eastern United States and Western Europe. And the positive phase of the NAO is typically associated with above normal temperatures in the eastern US. This happens in the wintertime when temperatures are really mild, very much above normal. Now, the negative phase of the NAO is when you have above normal heights and pressure across the high latitudes of the North Atlantic. So this is typically associated with blocking, and you'll have below normal heights and pressure across the central North Atlantic, eastern United States, and Western Europe. And when you have a negative phase of the NAO, you typically see below normal temperatures in the eastern US. All right, and I do have graphics to back up all of these teleconnection patterns. So let's go right to the graphics, starting with the NAO phase. So looking at the NAO phase, what you have going on, this on the left is the negative phase of the NAO, and this on the right is the positive phase. So with the negative phase of the NAO, you typically have a trough, a long wave trough into the eastern US. You typically have colder weather in the wintertime and even snowy. This is where you get your big time nor'easters, East Coast winter storms with this type of pattern. You usually have warmer conditions in the higher latitudes just to the west of Greenland, and also is typically associated with less sea ice because the temperatures are warmer, therefore there's less sea ice. But notice with the negative phase of the NAO, you have this huge ridge over the northern Atlantic, which acts as a blocking pattern. So you get these storms that form in the base of these long wave troughs, or just downstream of the trough axis. And basically, this block does not allow these nor'easters or East Coast storms, winter storms, it will not allow it to move off and out to sea. Instead, the storms hug the East Coast, providing for major winter storm events whenever the phase is negative. Now, the positive NAO phase, you notice that the jet stream is pretty much almost in a straight line configuration. It's not as amplified, there is no blocking, and look at the pressure patterns. You have high pressure over the central Atlantic, and then you have lower pressure up here near Iceland. But look at how this flip-flops between negative phase and positive phase. With a positive phase, the NAO, you typically have warmer, above normal conditions with more of a zonal jet stream, a more west to east oriented jet stream across the eastern U.S. and across the Atlantic as a whole. It's warmer and wet across Western Europe as well during this phase. So that is a good depiction of what you'd expect, the type of pressure patterns. This black line pretty much represents jet stream in both cases, the long wave pattern, the long wave troughs, and the ridges. Moving on now to the Arctic Oscillation. Now this is defined as a climate pattern which is characterized by winds circulating counterclockwise around the Arctic at 55 degrees north latitude. Now with this case, usually have basically when the AO is positive, you have a ring of strong winds circulating around the North Pole which act to confine colder air. It keeps colder air confined across the polar regions, so the coldest air remains bottled up over the pole. Now when the AO is negative, however, the ring of strong winds around the North Pole becomes much weaker and distorted, allowing for easier penetration of cold air further southward into the middle latitudes where we live. And so the polar front jet stream then becomes more amplified. It dips much further south with a negative AO, with increased storminess and Arctic air typically overspreading the eastern U.S. in winter. All right, so let's take a look graphically at the AO phases, the difference between negative and positive. With a negative AO phase, you typically have a much more amplified, and when I say amplified, I mean a very wavy or wiggly jet stream pattern from south to north and north to south and so on. So you get this big, this area of the jet stream really dips down to the eastern United States, typically have higher pressure up near the polar areas, higher latitudes in a negative AO phase. So with this trough, this long wave trough dipping further south, you get more penetration of cold air that comes down from the colder source regions of the Arctic and northern Canada into the eastern US. Now with a positive phase AO, the jet stream is more zonal, more west to east, not as much in the way of amplification of the jet stream, there's no major dips, troughs, or ridges at all with a positive phase. So it's more of a milder flow from west to east across the US, more of a maritime type air mass coming from the US, basically from the Pacific Ocean all the way across the US. All right, now we move on to the next oscillation we're going to talk about, and that would be the Pacific North American or PNA pattern. Now, what happens with a PNA pattern is it's a pattern characterized by comparing the long wave pattern between the western and the eastern United States, a trough ridge pattern versus a ridge trough pattern. I'll show that graphically here in a moment. Now with a positive PNA pattern, this is going to occur most of the time. It's a climatological norm actually, when there's a ridge over the western US and a trough over the eastern US, and it generally follows the natural topography scheme east of the Rocky Mountains. What I mean by that is typically you have a trough, a long wave trough, setting up from the Rocky Mountains eastward to the Atlantic seaboard. And that is because of how the terrain is naturally flatter over this part of the country. And the cold, dense air is more readily able to penetrate further southeast, just to the east of the taller Rocky Mountains, for example. Now, when the PNA becomes negative, this occurs when there's a trough over the western United States and a ridge over the eastern United States. So in this case, the pattern remains highly amplified, except we're just flip-flopping what it actually looks like. All right, so with a PNA pattern, it occurs in a highly amplified long wave pattern and may result in stagnant, stuck in place type extreme weather events where you have very warm conditions in the western U.S. and very cold in the east, or vice versa. So let's take a look at the PNA pattern now. So with the positive phase of the PNA pattern, what you have is a highly amplified jet stream. So you see this huge ridge over the western U.S. and this huge trough over the eastern U.S. So the cold is allowed to readily pour into the eastern U.S. with this huge ridge and this deep trough in the east, right? And then with a negative, it's just the reverse pattern. You get more of a troughing in the western U.S. in the long wave pattern and more ridging in the east. So it tends to be milder across the eastern U.S. with a negative PNA pattern and much colder with a positive PNA pattern. All right, now we're going to move on next to the El Nino Southern Oscillation. Its abbreviation is ENSO, slant La Nina. This is one that most everybody hears about on the news quite often. With the ENSO, it is a periodic fluctuation in sea surface temperature and air pressure of the overlying atmosphere. That's what the pressure difference is what makes it a southern oscillation. It's across the equatorial Pacific Ocean. The southern oscillation refers to a bimodal variation in the sea level barometric pressure, and 2 points are chosen in the Pacific: Darwin, Australia, and then the island of Tahiti. And to describe the El Nino Southern Oscillation, what is typically used is the Southern Oscillation Index, or the SOI. It's used to determine the standardized difference in pressure between Tahiti and Darwin. All right, so that's the El Nino Southern Oscillation, and it's associated typically, if you look down here on this chart, the edges here, these red lines indicate the El Nino the Nino 3.4 region, and this is where we look at sea surface temperature anomalies. If it's above normal, the sea surface temperatures, then we're typically in an El Nino phase, and if this area is below normal sea surface temperatures, we're in a La Nina phase. Keep in mind, La Nina is just the exact opposite of the El Nino Southern Oscillation. La Nina is basically when you have below normal sea surface temperatures in this Nino 3.4 region, right here, in the equatorial East Pacific. And then looking at the typical wintertime patterns for El Nino and La Nina. All right, for El Nino, you have this huge area of warmth that expands from southern Alaska all the way down to the Pacific Northwest, the northern plains and Rockies. All right, and you got a more active subtropical jet stream to the south. All right, I'm going to wrap up part 1 of this teleconnection video, and I'll be back again here in a moment with part 2.